Hello, everyone. I hope you are all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Pavel Kroupa, who is professor and leader of the Stellar Populations and Dynamics Research Group at the University of Bonn. My name is Elizabeth Artur de la Villarmois, and together with Thomas Putzia, we have organized today's webinar for you. As in our previous webinars, simultaneous language interpretation is provided by Patricia González, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym.
Thank you so much for all your feedback and comments again. We really appreciate it. If you're watching a recording of this talk on YouTube later on, please leave your comments below. If you would like to support the Golden Webinar series, send us please feedback and offers via email, if you will. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comment on them. And we will select then the best questions for the discussion after the talk. Again, the link of the video will be automatically taken down by YouTube shortly after the streaming is over. However, we will post the high resolution version, both in English and Spanish, later on in the coming weeks to the YouTube channel. So before we begin, we also would like to introduce our panel members that are with us today. Pavel, of course, Patricia, our interpreter, Elizabeth, and myself. From the faculty of the Institute of Astrophysics at Pontificia Universidad Católica, we have Gaspar Galas today with us and Alejandro Clocchiati. Also from the Institute at PUC, we have our postdoctoral fellows, Paula Ronco and Demetra de Chico.
We also have the great pleasure to welcome our guest panelists today, Teresa Jarabkova, Research Fellow at the European Space Agency, Nicole Benetti, Postdoctoral Research Fellow at the University of Naples Federico II, Indranil Vanik, Postdoctoral Research Fellow at the University of Bonn, Stacy McGaugh, Professor of Astronomy at the Case Western Reserve University, Sver Arset, Research Scientist at the Institute of Astronomy at the University of Cambridge, and Mordechai Milgrom, Professor of Astrophysics at the Department of Particle Physics and Astrophysics at the Weizmann Institute in Rehovot, Israel. And last but not least, we have our excellent Q&A manager, Simon Angel. So it is our great pleasure to introduce Pavel Kroupa as our Golden Webinar speaker today. Pavel studied physics and mathematics at the University of Western Australia in Perth and moved to Cambridge in the UK in 1988, where he obtained his PhD degree in 1992 at Trinity College as an Isaac Newton Scholar. After that, he took his first postdoctoral position in Heidelberg and worked until the year 2000 in astronomical research groups at Heidelberg University and at the Max Planck Institute for Astronomy. In the year 2000, Pavel moved to Kiel in northern Germany for his first teaching position, and he earned his habilitation there in 2002. After winning a Heisenberg Fellowship in Kiel, he accepted a professorship offer from the University of Bonn, where he is since 2004. And in 2017, he was named Professorem Hospitem by the rector of Charles University in Prague.
Pavel's scientific research focuses on the dynamical properties and evolution of stellar systems, star formation, dynamical evolution of open and globular clusters, origin of field stars, structure and mass of the galaxy, galactic dynamics, formation and evolution of dwarf satellite galaxies, and dark matter content of galaxies. He contributed to the derivation of the contemporary generally canonical IMF, initial mass function, which describes the distribution of the star masses at their birth, which carries his name, the Kroupa IMF. Among his scientific contributions, we can find the discovery of stellar dynamic solutions for the satellite galaxies of the Milky Way without the need of dark matter, and the formulation of the IG-IMF theory, the integrated galactic initial mass function. Since 2010, Pavel has become increasingly interested in and concerned with cosmology, identifying the challenges faced by the dark matter-based standard model of cosmology with their potential solutions and implications. He has been awarded the Silver Commemorative Medal of the Senate of the Czech Republic in Prague and the Crystal Rose by the citizens of his town of birth. Now I will have to pronounce this correctly, Jindřichův Hradec. So we would like to invite Pavel now to tell us all about his talk topic, From Belief to Realism and Beauty. Given the non-existence of dark matter, how do I navigate amongst the stars and between galaxies? Pavel, we're all ears.
Okay, great, wonderful. So thank you for having me, and I will begin with a prologue. Just a few statements which I think are necessary. So the words opinion and belief must not be part of the vocabulary in the natural sciences. A physical theory is mathematically well defined. The axioms of the theory are not its predictions. A physical theory can never be proven right, because for every confirmation by data, there can be many other theories which account for the same data. The physical theory is formally disproven if it fails to account for some data with at least 5 sigma confidence. That means the chance of it happening is less than 1 in 1.74 million. For example, the hypothesis that the Higgs boson does not exist has been falsified with at least 5 sigma confidence. Example 2, in my opinion, the Higgs particle exists is a non-scientific statement. A physical theory must be able to make predictions prior to the measurements or to account for new observations without parameter adjustments. And so as a citizen of the Commonwealth and a subject of the Queen, I pass through the gate to professional astronomy by counting stars. And my attempts to become an observational astronomer failed miserably. And moving from the island to the continent, I turned to computational astrophysics. My job being to compute how satellite galaxies thicken the Milky Way disk. And I quickly discovered entirely new stellar dynamical solutions to the dwarf spheroidal satellite galaxies. I wrote this paper in 1997 with the title Dwarf Spheroidal Satellite Galaxies Without Dark Matter. In this paper is figure 9, which shows a snapshot of one of the solutions, and this particular solution has an absolute visual magnitude of -9, a half mass radius of 180 parsecs, and a dynamical mass to light ratio of 200, which suggests to an observer that this object is completely dominated by dark matter. But there's no dark matter in this model. Remarkably, these numbers are extremely similar to Hercules, which was discovered in 2007. And so this is a real prediction 10 years before the discovery of this type of celestial object. What were the community reactions at that time? Well, I heard you are unhireable quite a few times. And my counter reaction was, well, there's something not quite right with the community. And once one leaves the dark matter framework, real and correct predictions become possible. And so the outline of this talk is as follows. I've just covered the prologue. I will now come to a ficture story. It's about 12 minutes. Then I will go on to the core and cover the scientific aspects, so the dark matter approaches, other approaches, and reach conclusions. And finally, there will be an epilogue. So please bear with me. A ficture story with elements of truth. So the disclaimer, partially based on real events, but the characters, names, and events depicted in the story are, of course, fictional. So not too long ago, Oumuamua passed the Sun on a hyperbolic orbit. It came close to the Earth to within about 1/10 of an astronomical unit, and went back out to the stars on a hyperbolic orbit. So on the sky, it looked as follows. It approached, and these ellipses are due to the Earth's motion around the Sun. So as it approached, the ellipses became larger and larger. Then it passed the Earth, and went back out to the stars. And we will now retrace the orbit. So we go back in time and see where it came from. So here's the Milky Way galaxy. You see the bar, and that's where the sun is. And retracing the orbit back, we find over here a star with planet Zamia. This is planet Zamia, and we have here the central country Bohia. We zoom in on Bohia or approach Bohia and find that it's a very beautiful country. Bohia is ruled by Král Vokrola. He rules over many different types of people, and the government is supported by Královská astronomer Subra and the nameless soldier. So these people have built amazing buildings. The ancient Bohia scientists learned how to engineer a drink with magical powers, the magical drink. Now, next to Bohia is Bavia. Bavia is governed by the Temne Král Bila and supported by Královská astronomer Spinga. In Bavia, they tried to copy the magical drink of Bohia. They tried to copy the buildings of Bohia. They still dress in animal skins. But admittedly, they have put up some impressive research infrastructure. So that's how this whole planet is governed, by all these different countries. And one day, Král Katoliga from Chile declares, with our many heavenly telescopes, my astronomer Putsa made a great discovery. They found over here a star with a planet, and we need to know what it is. And so we propose a galactic space mission to send a ship there. Everybody agrees it's a great idea. And Král Alka from Havia says we can build the ship using the Löba star sail, Löba being one of our cleverest astronomers on this planet. The Löba star sail works as follows. Photons from a source push the sail to high speed. Then Temne Král Bila interjects and says, no, we cannot navigate because the many dark clumps will throw the ship off course. As everybody knows, our galaxy is immersed in a sea of dark matter clumps or dark clumps which are orbiting here. This is a negative image, so each of these would be dark and unobservable. And this means that if we send a ship into this direction, there might be a dark clump in the vicinity and it will throw the ship off course. But we can't observe the clump, so we don't know which trajectories to send the ship in, nor do we know how much fuel to give the ship. The majority of countries agree with this. Just a minority says, no, we can still navigate. Král Alka from Havia confirms the Löba star sail will work, but then evil non-scientist Eth Ziga shouts out, I do not believe in Löba, whose ideas are wrong. The majority agree, just the minority still thinks we can navigate. Yes, we can navigate, confirms Král Vokrola. Our ancient astronomers, Tycho and Kepler, taught us how to navigate in the solar system. And today our astronomers use the Milgrom method from Weizsäcker. So if this is Bohia, then Weizsäcker is over here. And in Weizsäcker is governed by Král Nira, and Královská astronomer Milgra explains, for the interstellar ships, we must use this equation. So we map out the positions of all the stars and gas, that's this row, and then we can calculate by solving this differential equation the potential, and the gradient of the potential will tell us the forces which will act on the ship. And so we know exactly which course to send the ship on and how much fuel the ship needs to take along. It would be a catastrophe for the ships if we apply the simplified solar system equation given here. But then evil non-scientist Eth Ziga screams out, in my opinion, the Milgrom method is wrong, and dark clumps, of course, exist. The majority of countries agree, tensions rise, and in that moment, young astronomer Banica changes sides. The world at the brink of war. At that moment, the very wise philosopher Merita says, stop. Another war makes no sense. We have already waged a big war 4 times. Nothing changed. There was the Hussita War when all these armies descended on Bohia, and the country sprang back to life. Then we had the Wallsteiner War, and the country yet again sprang back to life. Then there was the Wilhelm and Adolpha War, and the country was rebuilt. And finally, we had the Covida War, and yet again, life came back. And so you can neither beat their magic drink, nor their sacred knedlike. Instead of a fifth war, I suggest a scientific competition. The vanquished will accept the other's theory. We predict the rotation curves of 1,000 galaxies, which will be measured by the telescopes in Chile, and then we measure the rotation curves. So here's how it works. We have a galaxy NGC 1560, where we map the stars and gas outwards as we go outwards in radius. So this is the plot down here. We have the stellar distribution, the surface mass density versus the radius in the galaxy, distance from the center. And we have the stellar distribution, which is an exponential disk, and the gaseous distribution, which we can obtain from radio astronomical observations. So we know the distribution of normal matter, that's the rho, and then we can solve this differential equation to obtain the potential. And once we know the potential, we can predict the rotation curve of this galaxy. And of course, in this case, we have to postulate these dark clumps. We can also use the Milgrom method to do the same calculations. So we know the distribution of stars and gas here, calculate the potential by solving this differential equation, and then predict the rotation curve to be like this. It depends on the mass of the stars within the radius r and the gas in the galaxy. So we can then make this plot, the velocity of rotation versus distance from the center. And depending on what the predictions will be, we can then apply the observe the rotation curve and verify which of these are correct. After many years of observations, the results became available, and here is what happened. So, for example, here we have this galaxy, and this is the galaxy we've just seen. So here we have the distribution of stars and gas out to radii of nearly 20 kiloparsecs, and the measured rotation curve appears like this. In this galaxy, the measured rotation curve appears like this. The predictions done before the measurements of the rotation curve, following the simplified equation, only give a range of possible rotation curves. The reason being that it only gives a range is because the distribution of the dark clumps is not well known. But then if we solve this equation by Milgrom, we obtain an exact reproduction of these, so the observational data exactly confirm the prediction. Even the predicted dips in the rotation curve are accounted for. And so the Milgrom's method wins. Those who failed the test must now memorize the book to learn how to do the calculations properly. It is known precisely how to launch the ship and which orbit it will take. The majority of scientists still think that dark clumps exist, and so they decided to, rather than learn the book, the believers in dark clumps decided to build the ship Dark Mainstream and to go out into space and search for the clumps, and to keep searching and to keep searching and to keep searching, because in their opinion, of course, dark clumps are there. So the Dark Mainstream left the planet to search for dark clumps. The remainders learned to understand the vacuum and to engineer it. Meanwhile, the Dark Mainstream lost its sail, and the sail approached our solar system, passed the sun and the earth, and then went out back to the stars. And this ends the fictitious story. I will now come to the core and cover the scientific aspects of this problem. So the standard model of cosmology is based on two fundamental assumptions and axioms. The one is that the Einsteinian Newtonian formulation of gravitation is valid everywhere. The Newtonian formulation is of course only valid in the classical regime. And the second assumption, which is very fundamental, is that all matter is created at the Big Bang. We then add observational data, for example, from the cosmic microwave background, rotation curves, to find that we need to add three auxiliary assumptions, which are inflation, dark matter, and dark energy. And I should note here that the dark matter here can be called warm, fuzzy, or axion. It doesn't matter because ultimately it has to behave in the same way. For example, in this theory, one has to account for little galaxies which have a size of only about 50 parsecs to be dominated by dark matter, which means that fuzzy dark matter must have a wavelength so small that it actually manages to fit into these small galaxies. Therefore, it then becomes very similar to cold dark matter on the scales of a kiloparsec. So we have this model where we have the Big Bang, then inflationary periods, and then the universe expands. And today we are experiencing yet again a new inflationary period through the action of dark energy. As the universe expands, the gas cools. We then see the cosmic microwave backgrounds when the photons decouple from the matter, and during this time, the dark matter is already forming the first gravitational bound structures into which the cooling gas falls, forms the first stars. The dark matter halos coalesce, forming larger dark matter halos into which more gas falls. Galaxies form, merge, form larger galaxies, and today we would be observing this universe, if this were the correct universe. So there are some uncomfortable properties. The dark matter particles needed in this theory are not part of the standard model of particle physics, and no experimentally verified extension of the standard model of particle physics exists. The dark matter particles have not been found despite an incredibly huge effort by many research teams. Dark energy is totally not understood. Does it constitute infinite energy creation? It is a total misfit to the vacuum energy density. Inflation has many issues, and this was a very interesting inflation debate by these authors published in 2017 in the Scientific American, which you might like to read up on. So according to the standard model of cosmology, galaxies look as follows. This is the observable part of the galaxy, stars and gas, and the galaxy sits in a dark matter halo, which has this type of scale for a Milky Way type galaxy, and the dark matter halo is composed of dark matter particles, but also many subhalos, dark matter subhalos. Again, these are actually black, but here, in order so we can see them, they are shown in a negative image. And these dark matter subhalos are orbiting around here and slowly shrinking downwards to merge with the central galaxy. It's a very dynamic life structure. New dark matter halos fall in as the structure grows. And this leads to us to an immediate fundamental dysfunctionality. 90% of all real galaxies are thin disk galaxies, but we cannot predict their rotation curves. So given an observed mass distribution, it is impossible to calculate the circular velocity of stars within it in the sense of a prediction. Why not? Well, this is here the answer. So here we are plotting on the y-axis the stellar mass of the galaxy, while this here is the dark matter halo mass of the galaxy, and each point here is one galaxy obtained from cosmological supercomputer simulations in this framework. And so, for example, our Milky Way has a stellar mass of about 10 to the 11 solar masses, and so it can have a dark matter halo mass of about 10 to the 12 solar masses, or it can also have a dark matter halo mass which is more than 10 times larger, but we don't know which it is because we can't observe the dark matter. Furthermore, the concentration of the dark matter halo is unknown. So this plot shows the log of the concentration versus log of the visual mass of the dark matter halo. So our Milky Way would have a dark matter halo mass of, say, 10 to the 12 solar masses, and it would have a concentration which is this small, or equally, it could have a concentration which is more than 10 times larger, but we don't know since we can't observe the dark matter. And so this essentially means as follows. We have the observed galaxy, and this galaxy can have some dark matter halo around it within a range of possibilities. It has a concentration, it has dark matter subhalos, and the radius and mass of this dark matter halo, which can be rotating this way or that way, and we don't know. And for this particular case, one might predict this rotation curve or calculate this rotation curve if we know this exact dark matter halo. But then the same galaxy might also have a dark matter halo which has this shape. And then it would have this rotation curve. And it might also have a dark matter halo of this shape. And then it would have this rotation curve. And so we cannot predict the rotation curves from the observed matter. That's the point, in this theory. Now, there is a prediction of a new phenomenon in this theory. If there is dark matter, then there must be Chandrasekhar dynamical friction. What this means is as follows. So we have here a Milky Way type galaxy in its dark matter halo with its concentration, and then another galaxy falls into it. And it also has its own dark matter halo. And as the galaxy falls through the dark matter halo of the host galaxy, this dark matter halo and galaxy interact with the dark matter particles in this galaxy. The interaction is purely gravitational, of course. So each dark matter particle here is deflected by the motion of this galaxy, which is entering the host, and is deflected. And the many, many deflections cause this galaxy to get slower, to slow down. We can visualize this by considering that these deflections cause a dark matter wake behind the galaxy, which pulls back at the galaxy, and so it decelerates. Now, after integrating all these encounters, gravitational encounters with all the dark matter particles, one finds this equation. It's a well-known equation in dynamical friction. And this tells us how the velocity of the galaxy is reduced per unit time. It depends on the mass of this galaxy and its dark matter halo. It depends on the velocity of this galaxy, and it depends on the mass density of the dark matter halo. Now note that the mass of the dark matter particle doesn't matter because it's the mass density which matters. So you can have massive particles or very, very low mass particles, but then you'd have many, many more very low mass particles. This quantity, the mass density of dark matter, is fixed by the cosmological model and the cosmic microwave background. This means that the dynamical friction has no parameter in it which we can tune. So we cannot, in this theory, increase or decrease the dynamical friction process. Once the theory is formulated, as it is now, given the data boundary conditions, this process is fixed. And so what happens is the galaxy falls in, forms a dark matter wake behind it, and falls further in as it loses kinetic energy and falls in and merges. And this is the reason why galaxies merge. But they only merge if there is dark matter. Because without dark matter, we don't have the dynamical friction, and then galaxies just pass each other. Now, this leads to an actual dysfunctional property, one, and that is that bars slow down due to dynamical friction of the dark matter halo. So we have here this galaxy with a very major bar in it, and this bar rotates like a solid body. And so it forms a wake behind itself as it's rotating in the dark matter halo of this galaxy. This wake pulls back on the bar and slows it down. And this has been studied by the research group of Mahmoud Roshan and Neda Ghafourian and others. And they find that the observed bar rotation to be in 8 sigma tension to the latest high-resolution Illustris and Eagle models. So one quantifies this parameter R, which is the length of the co-rotation. So you have a galaxy and in it is a bar. The bar is rotating like a solid body. And at that radius in the galaxy at which the stars rotate with the same angular speed as the bar, that is the co-rotation radius. And that distance from the center, one divides by the actual bar length. And if this quantity R is larger than 1.4, we have a slow bar. And if it's smaller than 1.4, we have a fast bar. The data are plotted here. So we have here the R parameter. this one here, and this is the dispersion of the R parameter. The observational data are here. So it shows, with this confidence contours here, it shows that real galaxies have fast bars. 1.4 is just over here. But of the theoretical galaxies with dark matter in the standard model, cosmological model, have slow bars, and the difference between the theoretical and the observed bars is an 8 sigma tension, and this disproves dark matter at very high confidence. Now, given that this is a serious conclusion with major implications for all of astrophysics, one wants to confirm this conclusion with independent tests, of course. One doesn't do one single test, but typically one would try to do additional completely independent tests to see if the results converge. And so here we can test this concept of dynamical friction by compact groups of galaxies, which should merge within 1 billion years. So you have, for example, here a Milky Way type galaxy, which has these other galaxies around it. The M81 group is very nearby. So we have the local group, and then just next door, a few million parsecs away only, it's basically the nearest galaxy group, is this M81 group. So we have good data for this group. You can see that these galaxies have interacted because the radio telescopes tell us that there's gas all over the place, and there's these gaseous tidal tails like over here and here. And so this type of data tells us that these galaxies have been interacting at least once to pull out the tidal tails, or they've been interacting multiple times. And so we can already see that this might be a tense friction because each of these galaxies is, in the theory, surrounded by a dark matter halo, which is bigger than this slide, each of these galaxies. And so these dark matter halos are sitting on top of each other and interacting with the galaxies moving around in there. There's massive dynamical friction here. And so this has been looked at by Yoon in 1999 and independently by Thomson, Lane, and Turnbull in 1999, and they found no solutions with dark matter because these galaxies merge too quickly and they can't distribute the gas as seen. They get solutions without dark matter. The galaxies just orbit about each other, pull out tidal arms and tails, and the gas gets distributed. And we confirmed this in our own work. And basically what one finds is that in order to reproduce the current situation of this M81 group, all the galaxies in the group must have come from a large distance to magically meet at instantaneously, basically at the same time, have one encounter before they merge, when we wouldn't see this group anymore. And so this basically means that this is arbitrary unlikely. Furthermore, we have many such compact groups of galaxies. And so this supports the previous conclusion. There's no significant dark matter halo in the nature. And so this is important because the conclusions are converging. If they were diverging, if one test would tell us there is dark matter, it's consistent with standard of cosmology, while another test would tell us it's not, then we would have a problem. But convergent conclusions are essential in this game to reach the strong conclusions which I reach. So we can continue with the testing by looking at the motion of the large and small imaginary clouds. We have here the galaxy, our Milky Way, with the center of it, Sagittarius, and this is the large and small imaginary clouds. The large and small imaginary clouds are moving past the galaxy with a large velocity, with something like 250 kilometers per second. The large imaginary cloud is at 50 kiloparsecs from the center of the galaxy, and the small imaginary cloud is at a distance of 60 kiloparsecs from the galactic center. They have interacted and also have left a long hydrogen trail, which is called the Magellanic Stream. So these type of data, so this is very similar to what's happened in the M81 group. So this type of data constrain the allowed orbit of these galaxies. So we have the following situation. We have our galaxy here with its dark matter halo. And then we have the large imaginary cloud with its dark matter halo moving past the galaxy, but this dark matter halo is within our large dark matter halo. And then we have the small imaginary cloud with its dark matter halo and within the dark matter halo of the large imaginary cloud and the dark matter halo of our Milky Way. So 3 dark matter halos on top of each other, and you can see that there's a lot of dynamical friction involved. And this is being investigated currently. The work is in preparation, but the results are very clear. There is no solution within the dark matter framework. The current positions and velocity vectors of these galaxies, plus the constraining fact that they need to be close and they must have interacted to give the magnetic stream, does not allow solutions with dark matter. Now, this tension is increased even more significantly because the Milky Way has not only these two satellite galaxies, but it has also other satellite galaxies which themselves have their dark matter halos and suffer dynamical friction. And this has been studied in 2011 in this research work here. And again, this conclusion here is that the then known satellite galaxies don't work with dark matter. Linked with this here, it's of course a massive falsification of the dark matter theory. Now we can look at other aspects of how this theory is supposed to arrange matter, because we can calculate it very well in supercomputers. We know how these structures form and the way these subhalos arrange themselves, and so we can observe the distribution, the three-dimensional distribution or the six-dimensional distribution in phase space of satellite galaxies and their equivalent in the dark matter model, and make comparisons. And so this problem was pointed out for the first time in 2005, where it was realized, or actually published, that the satellite galaxies are in a plane much like the planets around the sun. And then after that, Marcel Pawlowski and Oliver Müller significantly increased the research effort on this problem. And here's one figure from Pawlowski et al., which shows now a region of spanning 1 million parsecs times 1 million parsecs. And what we are looking at is, we are looking down from the North Pole downwards onto the Milky Way disk. You can see the Milky Way disk here. And its satellite galaxies are in this plane, forming a thin plane. And we are seeing also Andromeda. Andromeda is this ellipse here, and half its satellite galaxies are in an even thinner plane. And the remarkable feature here is not only that these galaxies have these satellite planes, but furthermore that the satellite plane of Andromeda is pointing at the Milky Way. And in addition to that, both planes of satellites are rotating in the same sense, which means that there's an incredible amount of correlation between these two satellite systems. So how can the Milky Way and Andromeda satellite systems be so correlated if there are subhalos falling in individually? So the idea and the theory is that all of these satellite galaxies have their own dark matter halos, and they fall in and merge with Andromeda, adding to the mass growth of these galaxies. But in that theory, it is absolutely impossible to have such a correlation between these two satellite systems. To make it worse, Müller-Pawlowski et al. Published the paper, A Whirling Plane of Satellite Galaxies Around Centaurus A. Centaurus A is again a very close by group. So we have the local group, then we have the M81 group just a few million parsecs away, and very close again, just a few million parsecs away, is Centaurus A with its associated galaxies. And the Centaurus A galaxy has a large population of satellite galaxies around it, which is in a thin plane, which is rotating. This proves that Milky Way and M31 planes of satellites are not unique. So this is not a looks elsewhere effect. In fact, since all the major galaxies in their very nearby universe where we can get such three-dimensional data seem to be in such planes, it shows that the planes of satellites are the rule, not the exception. And so combining the probabilities, so these are doing tests of these observed structures relative to the standard model of cosmological simulations like Millennium and Illustris, shows that there's a 5 sigma falsification of the dark matter models. And there's no significant dark matter halo around the Milky Way. So the Milky Way could not have formed from many mergers of subhalos because the remnants of this merger process is simply not evident on the sky. Making it worse, we now zoom out and look at the whole local group. So we are seeing here is everything we know about the local group. This is a region of space of 3 million parsecs times 3 million parsecs. This encompasses the whole local group. The whole local group is defined by all those galaxies which are gravitationally bound to each other. If we go beyond the local group, we find the Hubble flow. What we are doing here is we are looking along the line joining Andromeda and Milky Way. Andromeda and Milky Way, that's just here. So this here is Andromeda, and this here is the Milky Way. These are the satellite galaxies of both galaxies. All other galaxies in the local group are arranged in these two planes, which have a thickness of about 50 kiloparsec and are about 2 million parsecs across. The system is very symmetrical because the distance of this plane to the center to this line is equal to the distance of the other plane. So we have the line joining Andromeda Milky Way, and all the other galaxies which are not satellite galaxies in the local group are in two planes which are arranged like this, symmetrical around the line joining Andromeda and Milky Way. And this whole structure is moving like that relative to the CMB, which is this arrow. You see everything else is empty. And I call this a frightening symmetry because to my eyes, this is frightening. How can nature produce such a crystal-like structure on a scale of millions of parsecs, which is a Hubble time old? Clearly, this is not the smog at infinite sigma confidence. Zooming out even further, now looking at the region around us of 16 times 16 million parsecs, where the local group is just in the center here, and each point is a galaxy, we find that the local void is too empty, and large massive galaxies are too far from the sheet. So we have here the sheet, the void is far too empty, and there are massive galaxies which are far too far away. These are Milky Way mass galaxies, roughly. Now, the problem is that according to the standard model of cosmology, massive galaxies need to be in the sheet because that is where the matter is from which they form via mergers. So there's nothing here for them to form, but they are still star forming, so they're obviously growing right at this moment. And now we come to actual real cosmological scale tests, looking at massive colliding galaxy clusters at a high redshift. So we have here the Bullet cluster and the El Gordo cluster. The Bullet cluster is at the redshift of 0.3 and has a mass of 1.9 times 10 to the 15 solar masses. There are two clusters which have penetrated each other and gone out again and left the gas in between. So we can see this bow shock. This is the X-ray emitting gas here after the collision. The gravitating mass is shown here in blue as obtained from a weak lensing analysis around these clusters. Then we have the El Gordo cluster, which is at the redshift of 0.9 and is 10 times more massive than the El Gordo, the Bullet cluster. The El Gordo cluster again has two clusters which have collided and penetrated each other, leaving this double lobe of X-ray emitting hot gas. And the question now is, within the standard model of cosmology, can one produce such clusters at these high redshifts? And this has been studied by Elena Asensio and Indra Nilbanik to a great extent. So the question or the problem to be answered is we start at redshift of 1100 where we see the CMB, the cosmic microwave background. This gives the initial conditions for the cosmological model and structure formation. We then evolve the universe, use the big Jubilee supercomputer simulations for this, to see whether along the time as the universe evolves, one can find such massive clusters. And the result is that it doesn't work. In fact, the existence of these two clusters falsifies the standard model of cosmology with more than 6 sigma confidence. The details are in this publication. We can now perform another cosmological scale test. We count now the matter density as we go outwards from the local group. So on this axis, we have the distance from the local group out to 800 million parsecs. And we measure, as we go outwards, the mass density of galaxies. So per unit volume, how much mass is in galaxies. And as we go outwards from the origin here, we see that the matter density increases, reaching at a distance of about 400 million parsecs, the average density which the universe is supposed to have. This gray region indicates the allowed range in the standard model of cosmology, and what we observe is a massive underdensity on a scale of something like 400 million parsecs. This is called the Keenan-Barger-Coe void, and Modest Hasselbauer and Inral Barnick have been studying this to a great extent. And so in this research publication, the question is, we want to test how often does a KBC void occur in the standard model of cosmology. For that one, we used the Millennium XXL supercomputer simulation, one of the largest ones ever performed, with a span here of a box of about 4.2 gigaparsecs. And you can see, so this is now the snapshot at redshift 0. So this is the local universe. You can see here there are underdensities which actually do form. And there are overdensities also which form as a consequence of structure formation. And to answer this question, one constructs a volume with a radius of about 400 million parsecs and measures the amount of the mass density within this volume and compares this mass density with the average. And one does this 1 million times or so. And this is the distribution of these density fluctuations. So that's the frequency, and that's the density contrast parameter. You can see 0 means that the volume is at the mean density. If it's at this point, it's an overdensity in the volume. If it's at this point, it's an underdensity in the volume. Okay, so this is the distribution which is allowed by the standard model of cosmology. And that's what the real void actually looks like, with a much, much more pronounced underdensity. The difference between the theoretical distribution and the observed void is a difference of more than 6 sigma, which means that the standard model of cosmology is falsified with this test at more than 6 sigma confidence. So we have the void, and we are ourselves in the void, not at the center, but somewhere about a third or so, maybe halfway out. Now, from the void, we can see that the galaxies are falling towards the void edges, towards the void walls, because the gravity pulls them there. So from our point of view, the universe appears to be expanding more rapidly, which means that the mere existence of this KBC void automatically solves the Hubble tension. The Hubble tension is not a tension, it's actually a logical consequence of the fact that there is this void. However, this does not help the standard model of cosmology, because the KBC void is not possible in the standard model of cosmology. And this is what we've tested. We've taken the boundary condition, again being the CMB, moved to the present time with the Millennium simulation, as I've just described, and found that such underdensities on that scale, 400 megaparsec radius, are excluded in the model at more than 6 sigma confidence. Note that Kenworthy et al. Argue that the KBC void is not possible because they don't see evidence for this motion, this expansion in the supernova 1A data, but they made an error in the analysis, and that error is discussed and explained at length in Hasselbauer et al. 2020. So this massive underdensity on this large scale is seen in quite a few other surveys. We see it in optical galaxy surveys. We see it in the infrared. Of course, that's where the name comes from. We see it in X-ray cluster surveys, and we see it in evidence from the CMB dipole of large-scale bulk flows expected for such a void, and there are these publications which report that. Furthermore, there's much evidence for highly significant over and underdensities in galaxy cluster data. This is the nice work of Mikas et al. And there's also 4.9 sigma exclusion of the cosmological principle based on the distribution of 1 million quasars by Sekres, Sarkar et al. And so there is no dark matter. This is absolutely clear from the data. Galaxies therefore merge very rarely, if ever. I mean, to merge a galaxy, they'd have to really physically collide in terms of the physical observed matter. And what about dark energy? So the evidence is thus that the real universe is far more structured than allowed in the standard of cosmology. As the universe evolves and these voids build up and also overdensities build up, larger and larger fraction of the universe is occupied by these voids. The voids expand more rapidly, which means that an observer within the voids will see, as the voids reach a critical fraction of the volume, that the universe appears to suddenly start to accelerate its expansion. And this has been shown by David Wiltshire. So cosmic acceleration is an apparent effect due to the over and under densities in the universe, which are far greater than allowed by the standard model of cosmology. Now, it's basically the same effect as the Hubble tension, which is an apparent fast expansion, except it is on much larger scales. Observed from a deep void, the universe is older than viewed from a galaxy cluster. And so there doesn't seem to be dark energy. And what now? We have to now turn to non-dark matter theories. The observed lack of dynamical friction, so from the tests I've just mentioned, plus the observed much larger density contrasts on large cosmological scales, clearly show that we need an effectively stronger gravitation to describe what's happening out there. But all hybrid and other approaches which mimic the success of the standard model of cosmology on large scales, larger than 50 million parsecs, for example, through dark matter, are immediately ruled out with equal significance and the standard model of cosmology by more than 5 sigma, by the mere fact that we have the void, KBC void, and we have these massive clusters. I'm very sorry for this. This is one is not doing this on purpose to rule out theories, but that's the job of our scientists to learn how the nature works on the basis of the data situation. This leaves only a few possibilities. For example, modified gravity. It's a covariant modification of Einstein gravity. The theory introduces 2 additional scalar fields and 1 vector field. So it's an approach, an attempt to explain what we observe without dark matter. And this has been studied in this research paper by Hossein Haggi and Akram Hassani Zunusi et al., based on dwarf galaxies. Then there's emergent gravity, which essentially means that gravity is a consequence of the information associated with the positions of material bodies. And this has been studied by Lely et al. In this research paper. And then there are the gravitational dipoles idea, which I actually like very much. It's if antimatter anti-gravitates, matter-antimatter pairs resulting from quantum vacuum fluctuation would be virtual gravitational dipoles. And this, so the dynamical discrepancies in galaxies are an effect of gravitational polarization of the gravitational dipoles. And this has been studied by Barnick and myself using solar system data. And then there's the scale invariant GR, so which is based on Wales integrable geometry endowed with a gauge scalar field. And this has been studied by Indra Barnick myself using just the Earth and the Moon system. And so as a summary of these non-dark matter theories, we can say that emergent gravity is significantly challenged by the radial acceleration relation data. Modified gravity is falsified with more than 5 sigma confidence based on the properties of dwarf galaxies. Gravitational dipoles is falsified with much more than 5 sigma confidence based on solar system data. And as the scale invariant GR is falsified with more than 200 sigma confidence based on the Earth-Moon motions and dynamics. And this leaves us now with Mont and Milgromian dynamics, which is a generalization of the solar system dynamics to the scale of galaxies. A formulation in the classical limit is known and is energy and momentum conserving. So in this seminal paper by Bekenstein and Milgrom, they write down the Newtonian Lagrangian of the gravitational field, generalize this, so they write the most general modification of this Newtonian Lagrangian is this form. So you can see that this term has been replaced by this term, where f is now a function of this gradient phi squared. Extremizing the action of this, one can find the generalized Poisson equation. We've seen this before. This is the mass density of the observed matter, and that spawns this field phi. Now, such an equation is known from some classical theories of quark confinement. This function mu, which transits the gravitational law from the Newtonian regime into the extremely weak field regime, can be derived from the quantum vacuum, as shown by Milgrom. Very important is to note that Mond was motivated by the flatness of a few Milky Way type galaxy rotation curves known prior to 1983. This is very analogous to Newton being motivated by falling apple and the moon's motion. The predictions of rotation curves for low surface brightness galaxies were successfully verified much later. At this time, these galaxies were not known to exist, and yet the same theory explains exactly these galaxies. It is wrong to claim that Mond is phenomenological and was designed to only fit rotation curves. This is a wrong statement. It is wrong to make that statement. So what is Mond? Is it a new symmetry? Milgrom discusses the space-time scale invariance properties of it. One can argue that Einstein's GR is completely valid, and only in the extremely weak field limit are the equations of motion changed by process in the quantum vacuum. There's an analogy on this, which goes back to internal mechanics. Imagine that you've got a trampoline and you put weights on it. So we make this graph, depth versus the weight which we put on the trampoline, and so we have a heavy weight, less, and even less weight, and so the heavy weight creates a large depth here, and a lightweight, a smaller depth. We make a model. That's our model of this dynamics here. And then the question is, if we extrapolate this to very low masses, will this work? Of course, it won't work, because molecular forces begin to play a role here. And this is reminiscent of what we see in nature. So this plot shows the theoretical acceleration here and the observed acceleration here. For example, we look at Jupiter and we can calculate the acceleration on Jupiter from the Sun, because we know the mass of the Sun, right? So this is this number here. Then we observe the orbit of Jupiter, and we can calculate the acceleration needed to keep it on a circular orbit, and that's this number here. The solar system, of course, is exactly on the one-to-one line here, because Newton derived the theory based on this data, and Einstein had no other data too. If we now extrapolate the Einsteinian Newtonian gravity law to very, very low accelerations, we see these departures here in the galactic regime. This is the radial acceleration relation. It is completely predictive. There are many publications. So we've seen this before. By solving this equation for the observed matter distribution, one can even derive these wiggles in the rotation curves, which is not possible in the dark matter framework. The planes of satellites are easy as pie. We have interacting galaxies, not merging galaxies, but interacting galaxies that throw out tidal tails from energy and angular momentum conservation. In these tidal tails, new dwarf galaxies form, as seen here. And once they form, what can they do? They have to orbit in a plane, and that's what makes these planes of satellites. The KBC void and Hubble tension is not even an issue. You take the boundary condition of CMB, do a Mond cosmological calculation, and you get such voids for free. Plus the tension, of course, is automatically covered because of the void. L. Gordon bullet cluster, trivial, exactly the same. You just form them in a Mond cosmological model. Because gravity is effectively stronger, so more quickly can one build larger density contrasts. And so the equations of motion in Mond account for observations on scales from 100 parsec to gigaparsec without parameter adjustments. And this is a most remarkable success of modern astrophysics of great historical meaning. There are Mond predictions. So for example, on a scale of less than 100 parsec, one can look at wide binary stars. So Xavier Hernandez has been looking at this with these research papers. The idea is that if you observe very wide binary stars in the galactic field, they should show the effects of Mond by being effectively stronger gravity. So the motion should be faster. And this is being readdressed by Andrei Barnik with these research papers. And I think there will be much to be heard of in this on this topic in the near future, given the Gaia data. there's a prediction of a new phenomenon, which is called the external field effect. So we have here a galaxy with stars and gas around it on a scale of 50 kiloparsecs times 50 kiloparsecs. And if we plug this distribution into this equation here, into this row, we can calculate the Milgromian potential, which then tells the gas and stars how to move. We can rearrange this equation into this form, and if we then take the divergence of this potential, subtract the observed stars, stars and gas, the normal matter, we get the phantom dark matter density, which is shown over here. So the galaxy which you see here spawns around it a halo of mathematical halo of particles, which are not real particles, which is spherical, and it is a logarithmic halo. It also creates some phantom dark matter halo in the disk. So a galaxy spawns around it a phantom dark matter halo, which are not real particles, it's merely the extra Milgromian gravitational potential. And so we can calculate the rotation curve precisely just from the observed matter. If we now put another galaxy next to this galaxy, the dark matter halos shrink, this phantom dark matter halos, and the rotation curve decreases. And so halo shrinks and galaxies become more Newtonian. Rotation curves decrease at large R when other galaxies are nearby. So we can formulate an observational test. Is the shape of the rotation curve correlated with the amount of matter around a given galaxy? And this has been looked at by Hossein Hagi and Akram Hassani Zunuzi, finding evidence for this in 2016, but then readdressed by Khe in this research paper in 2020, where they used very, very fine superior observation data, and they find an 8 sigma detection of this effect. So the inertial mass remains unchanged, but the gravitating mass depends on the surrounding matter distribution. This has the implication that systems which should be round become droplet shape, and this has been studied by these people in 2010-2017 by Xufeng Wu and Hongsheng Zhao, and readdressed by Guillaume Thomas in 2018. Effectively, a globular cluster further away from a galaxy or a dwarf elliptical galaxy would not be spherical, but would actually achieve a teardrop shaped, and this can be tested with observations. Simulations are being performed. Graham McCandless is leading a cosmology group in Chile to do Mond cosmological simulations, and in Prague, Bonn, Strasbourg now, we're doing galaxy formation simulations. So you take a post-Big Bang gas cloud, allow it to collapse, it has angular momentum, it forms automatically exponential disk galaxies, which are on the radial acceleration relation. And we are now doing cosmological simulations. So you see here 2 boxes. They are initially identical. It's a span of 10 times 10 million parsecs, filled with gas, post-Big Bang gas. And in this case, there's an external field from a larger structure nearby acting on this volume. And you can see the difference. 200 million years after start, the first galaxies begin to form. You can see how galaxies appear in this simulation. In these sheets, voids form. The same on the right. But you can see that on the right, we have fewer galaxies and lower mass galaxies. And so in Mond, structure growth self-regulates through the external field effects. And this is a newly discovered process affecting structure formation, studied by Mosel, Hasselbauer, and Barnick. Very important, the CMB can be modeled in a relativistic Mond theory in which gravitational waves travel at the speed of light. And this is profound mathematical research done by Skordis and Zložník in Prague. And so the conclusions here are that we have many tests, and all of them are a complete and utter and total disaster for the standard model of cosmology. Mond sails through, it seems, perfectly. There are some question marks where research still has to be done. The standard model of cosmology makes a prediction, which is Chandrasekhar dynamical friction. It's a failure. We don't see it in the data. Mond makes a prediction, which is the external field effect, and it's a massive detection and a failure for lambda CDM because the effect cannot exist in this theory, and yet it's observed. And now a naive question. Put on your seatbelts. Is the CMB really the CMB? This is where panic and havoc breaks out in the community. The CMB is sacred. So the first stars formed in dense clusters. We studied this in this paper here by Yerabkova, and in this paper where we show that quasars and supermassive black holes very, very trivially actually form in the universe. And what happens is the following. So 200 billion years after the Big Bang, the first star clusters are composed of these massive stars, and also low mass stars most likely, but in a very compact configuration, less than 0.5 parsecs, and they are in binaries. Now these will merge. So within much less than 1 million years, the stars merge and throw out matter. When two stars, massive stars merge, they throw out matter which is nuclearly processed, so already enriched in heavy elements. And then the matter is blown out through the radiation field and winds of these massive stars, and dust forms. So today we have dust between the galaxies, ancient dust, and the dust absorbs starlight from the galaxies and re-radiates it in the infrared. And this has been measured. So we see here the observed extinction magnitude versus redshift, as documented by these people here and in this paper. And you can see that as the redshift, as you go to higher redshift, you see that the universe seems to be getting more and more opaque. Then Wawrzyk took exactly this dust and calculated all the photons which come from this dust, the infrared photons in an expanding universe, and finds in Prague that the sum of the photons across the universe from this dust makes the CMB, including all these fluctuations. Now, and there's a video which explains this research paper by Wawrzyk, which you can look at, by Rachel Parziale. So the cosmological dust origin of the CMB may be supported by CMB anomalies. You can see here in this paper by Schwarz and Starkman et al., they report 3 anomalies. There's a lack of more than 60-degree correlation. So you look at the CMB and the fluctuations are correlated, but once you come to the angular separation of more than 60 degrees, there's no correlation anymore. There's a mutual alignment of the lowest multiple moments, which is also seen in supernova 1A data, and there's hemispherical asymmetry, also seen in galaxies. Now, 1 and 3 may be solved by dust because dust forms after the Big Bang, while if the CMB is of inflationary origin, you expect all scales to be correlated because they were causally connected. But if dust forms after the Big Bang, then you get these scales to be non-correlated. And 3, of course, you would expect one side of the universe to be maybe a little bit dustier than the others. And so this has very, very deep and fundamental implications for cosmology, of course. And so that's why this would cause and causes panic. And now I'll come to the epilogue. So we have a problem. The problem is neither the data nor the theories, but it is sociological. The standard dark matter-based cosmological model is the most falsified model which the very vast majority of scientists have ever believed in. Never in the history of humankind have there been so many modern Ivy League educated researchers who have together erred so badly. This is a completely unique scientific crisis in history. The robust falsification of the standard model of cosmology is not new. In 2010, we published this paper, Local Group Test, and in 2012, this paper was published, which is called Falsification of the Current Standard Model of Cosmology. In this paper, I put up this graph. So this is the log of the confidence as a function of time, and this is where the model was created or thought up, formulated mathematically. In 1980, there were the first failures. We had to include dark inflation and dark matter. And then there were 2 real failures, and then we had to include dark energy. So in total, the steps down are 22, but only 19 count as failures because these black ones count as evidence for new physics. Now, if we are very conservative and assume that with every step downwards, we lose 50% confidence in the model, then by 2012, the remaining confidence was 1.9 times 10 to the minus 6. Which means that by 2012, the dark mainstream was well sunk already. And then we have to add the recent falsification based on the KBC void, Hubble tension, El Gordo cluster, bullet cluster, which each individually are more than 6 sigma falsifications. Independently of this, Eleonora Di Valentino has been investigating cosmic discordance and found that, taken at face value, the Planck data provide a significant indication against the flat lambda CDM scenario. Not fitting practically half of the current cosmological data is undoubtedly a significant blow to the LCDM model. And for a comprehensive review of the Hubble tension, they wrote this remarkable publication, and they write that there is a strong need for an alternative physical scenario beyond lambda CDM. And so we have the most falsified physical theory ever in human history, which is still believed by the majority of physicists. This may well be the greatest scientific crisis in all of history. Here's an example. In July 2014, this particle physics booklet was published. This is a regular publication which lists all the particles, their excited states and interactions, and there's a long section on dark matter here. It states in the first sentence that the existence of dark matter is by now well established. In 2015, I wrote to the editors and authors and suggested to amend this statement with this statement: the existence of dark matter is a leading hypothesis. This is a true statement. This is not a true statement, but my suggestion was blatantly rejected. It seems that respectable physicists today know dark matter exists. And so the question to ponder is, what is the role in the stagnation of over-invoking authority, Ivy League institutions, hierarchies, prestigious awards and prizes, extreme competition for research money, prestigious journals? One can put up this graph. Here I have discovery of new laws of nature per unit time per active researcher versus time, and today we see that the society is becoming more grant and award oriented, and I think there's an anti-correlation. I think today scientists appear preoccupied with getting awards and grants. And so you can believe in dark matter, but it doesn't matter in the real universe. The first ever detection of doesn't matter. And what does matter is Milgrom's generalized Poisson equation, which underlies the beauty of galaxies and the real richness of the universe. And with that, I want to end by wishing you na zdraví, to the restart. So thank you.
Thank you very much, Pavel, for this wonderful presentation. We will take a 2-minute break. All right, so we're back with a very well-prepared Pavel.
40 months myself.
Well, I don't think this is very necessary. We are very civilized here. So let's start with the Q&A. Thank you very much again, Pavel, for a wonderful talk. We will go to the first question in the Q&A, and it's asked by Giuseppe Saracino, who's asking, is it possible to find a link between Mond and extended theories of gravity, like for instance, FR gravity?
Not to my knowledge.
I can answer that. So, well, f of r, just formally you can see f of r, the r inside the f of r is the Einstein, is the scalar curvature general relativity constructed from the metric. So it tells you basically that for general relativity, you simply have f of r equals r. Okay, otherwise you generalize to some function of r. But this means that you modify gravity according to the value of the curvature, whereas Mond modifies gravity according to the acceleration, which is a completely different quantity, different attribute of the system. So offhand, you see that the two are not related. But having said that, there were attempts to somehow go around this obstacle. I think the attempts are not very successful, but people did try, but not in a natural way. So if you just consider a straightforward answer would be no, I think.
Okay, let's go to Teresa.
Thank you. So my question is, basically in a nutshell, the conclusions that you posted are there is no dark matter, no dark energy, and the CMB is just a dust. if we assume that you are right, what should we do apart from panicking?
Yeah, thanks. Well, that is indeed now the problem, right? I think it's not difficult to proceed. One just has to look at the nearby universe, learn how galaxies function, and work one's way outwards to see how the galaxy populations change with distance and independence of the density, and build up a new cosmological model, of course, whereby one would use as the stepping stone. Of course, Mond will not be the only part in this endeavor. One will have to accept potentially very different dynamics for the universe. So this includes the question of where does matter come from. So this is why the processes in galaxies are very important to know. So how quickly does gas consumed into stars, and where does the gas actually come from to sustain this? Because the majority, 90% of all galaxies are actually star forming at a very peculiar rate, which depends on the mass of the galaxies, right? And such data information will have to be acquired, used, and seen how one can generate models and theoretical descriptions, maybe even going back to ideas of Dirac and others. But it will have to be very, very different to what is currently thought to be the case.
If I may add something to this, Pavel. So there are also differences in our camp. So we do not all agree on everything, of course. My view would be that the evidence you brought up against dark matter are very robust, but the evidence against dark energy is much less so. And in my opinion, the energy against the CMB is even much less than this. So, you know.
Yes, no, I completely agree. I mean, absolutely. So the problem I see, though, is that the dust is there, right? And one has to take account of that intergalactic dust.
Yes, but the CMB is also there. I mean, it has to be there. If there was a Big Bang, there has to be some CMB. So.
Well, that's the basic implication. So if I take the dust and I obtain a photon flux which agrees with the CMB, then I have to subtract that photon flux from what is measured as the CMB, and what remains would be the evidence for a Big Bang, right? Or one can argue, or one should have to argue, that the dust is not there. That's difficult because it's been measured. And so I see very serious problems there, actually. You know, I cannot today anymore argue, as I did say 3 or 4 years ago. Today, I really cannot say anymore that the CMB is truly what we think it is. I had always cherished the CMB as the most significant evidence for a hot Big Bang, but unfortunately, then Wawrzyk published his paper, and I've looked a little bit at the empirical evidence, and that dust seems to be there. I've talked to some observers, and it is there, you know, and so one has to deal with that dust. And at the moment, I simply don't know how to deal with it, in the sense, you know, one can't just subtract it out of the equation because it's a physical reality. But I completely agree with you. I mean, it makes a lot of sense to have a Big Bang, but, you know, a lot of sense in what sense? Is it because we are accustomed to think that way? I mean, which model actually makes sense in that sense? I mean, so the only cosmological model which supposedly was to function is the dynamical of cosmology, and that's dysfunctional. That's completely clear. And so everything else is now at stake.
Yeah, but you agree that the universe expands, and, you know, the expansion rate is finite, and we know what it is. And if you extrapolate back,
I think as a scientist, one has to question everything, but it's important to find direct evidence for various physical processes. And so the expansion, so the interpretation of redshift being as a consequence of expansion, is the only currently known interpretation physically. But it would be great to have direct evidence for expansion of space. And I think we have that. I think we can show that there's a very strong argument that there is truly expansion of space. In fact, based on the local group. I'm in a project actually looking at that. So I'm pretty convinced space expands, yes.
Okay, the next question is from Alejandro.
Yeah, nice talk and very challenging to the mind. I don't think it is the biggest crisis in this regard in the history of humankind, because some 400 years ago we were going through something very similar. But the question specifically is the age of the universe. One of the things that gives strength to the standard cosmology that we have in mind is a convergence of very different observations. And one of them is the age of the universe, which I don't know, makes sense with the expansion that you measure. It makes sense with the cooling of a hot Big Bang, etc. How does fits in this new paradigm of the?
Yeah, well, first, let me just say that what I mean with the greatest crisis is in the certain sense that such a crisis has never ever been there. Not 400 years ago, because 400 years ago, the few researchers which actually existed who were doing true research in a scientific sense, they had to fight with completely different types of problems, like religious issues, and that's a non-scientific issue, right? So that's where belief comes in. Today we have the very unique and first time ever crisis where we have a very large population of highly educated scientists on this planet, which never was so large as it is today, and yet we have a complete massive failure of the system. That's the crisis, and that's never been there like that before.
Okay, I see what you mean.
It's exactly, yeah. The daily being daily confronted with people who know there is dark matter is the crisis, yeah, and the inability to actually explain or them to accept these problems. At least this is my experience. And so the other issue of the of the new paradigm, well, there is actually no new paradigm. That's the problem. I mean, we're sort of stumbling into it and working into it. So in particular here with Indranil Barnik and Niels and Benoit Famey and Candlish in Chile, we have looked at a possible advance, and that is we still take the completely standard expansion history of the universe. We assume there is a hot Big Bang with the CMB being what is currently thought it is, and we then perform computations but without dark matter, without cold dark matter, of an expanding universe, to study which type of structures form in that, and to understand whether voids like this void can form, or these clusters can form. So that is the first step. We of course have to be very conservative. We can't at the moment invent some completely new paradigm, because it simply doesn't exist. You know, this new paradigm might indeed include, I'm really just speculating here, might include going away from the hot Big Bang. I mean, in the past there have been such ideas, but they've been thrown out because of other observation evidence. But one should never say no, as I would say. Yeah? And what I find worrying, and this is what has been covered in one of the golden webinars, actually, by Ruffini, I think it was, that the question is, how do galaxies acquire the mass over the history such that they have essentially constant star formation histories, which the star formation rate depends on the mass of the galaxy, and it seems to be constant. And how do they acquire the angular momentum over 10 billion years consistently and constantly? Yeah. And that is, I think, a great challenge, a big challenge. We are looking at these issues now with Moritz Hasselbauer and again Indranil Barnik and Niels Wittenburg. And what do the current cosmological simulations tell us about this process? So illustrious eagle simulations. And we are now explicitly doing Mond calculations in respect to address the question whether in Mond, where we get what it seems about the right structure formation, so the density fluctuations seem to be about right, we get the galaxy clusters, but do the galaxies which form in a hot Big Bang model, but then with Monds, do they behave like the real galaxies? And that's a current hot question we are addressing in the group, and it's not easy to address because in Mond simulations, the galaxies form out of gas. And you don't have particles which have a label, so you can't actually trace the emerging behavior or how galaxies form. You have to invent some new algorithms, and that in such very small groups is a big challenge, a computational challenge. So we will have to build up a new paradigm, I think.
Okay, next question is from Gaspar.
Thanks, Elizabeth. Hi, Pavel. Well, this was an excellent talk, and I'm happy to be here. I agree completely on your affirmation that we are living a crisis, and perhaps it's a much more bigger crisis than Alejandro mentioned about 100 years ago. Perhaps he was referring to the ether, right? If the ether did exist or not. But I think here is a larger crisis, because a lot of money has been invested in develop the dark matter theory, the simulations, a big army of people, students, postdocs, millions of dollars invested in developing a theory, which is now a big building in which all of us, including myself, are working in some way. And the problem is, how you think we have to, or because now I am trying to be as objective as possible, but what is the key step to convince finally the whole group of people working on believing that dark matter is the correct way? And another thing I want to comment, or a second question, is you mentioned a lot of things where it's impossible not to be convinced that the theory of Mond is correct. It's impossible to say that is all false. Of course, the proofs are there in the publications, but you didn't mention, for example, the one of the things that is one of the strongest proofs of dark matter, that dark matter should exist, and that is the gravitational lensing in big clusters, right? How can I explain a student that the dark matter doesn't exist and doesn't cooperate to produce the gravitational lensing in clusters?
Shall I first go on? So try to answer the lensing point. So there are two issues. The one is that the lensing has to be done in a different gravitational framework, right? So it would be a relativistic Mond theory. So one has to reanalyze the lensing data, not in GR. Weak lensing data. Strong lensing would be the same, yeah? And that's one issue. And so I'm not sure what the outcome of that is. It's true, this is what I've heard. I've not worked in that field, but in Mond you can even get negative mass densities apparently. Yeah? So I mean, just the way the lensing works, you would get regions around, say, galaxy clusters, which would even look like negative mass densities, and so that could be looked for in observational data, but one would have to go back to the raw data and reanalyze them with a different gravitational framework.
May I add to this later? Okay, you go on. I'm sorry.
Okay, sure. But yeah, so then it's true that galaxy clusters appear to have a mass deficit in Mond. So you see that in the motions of the galaxies in the clusters. Galaxy clusters, there is something like a factor of 2 mass missing even in Mond. Yeah? And that can have a variety of reasons. What I would prefer to argue is to say that most of the mass of a galaxy cluster is in the X-ray emitting gas. It's basically one huge plasma ball with a few galaxies orbiting within it, and so this gas is X-ray emitting, so it's cooling profusely, obviously, otherwise it wouldn't be emitting, and so there must always be some cold component in there, and that might not be detected. Yeah? And I'm not sure if this could make a factor of 2, but it's entirely possible that the gas is cooling but then being reheated. Yeah, I don't know. And then it's of course possible that there is dark matter in the sense of the normals. I mean, standard particle physics dark matter, so neutrinos. Yeah? Not normal, not the 3 normal neutrinos, but the stellar neutrinos. Now we know that neutrinos change their masses, and in that framework, one has suggested there's stellar neutrinos, and the stellar neutrinos could have a mass of something like 10 or so electron volts, and then it would just fit perfectly, and it would even be consistent with the standard model of particle physics, as far as one can say that the fact that neutrinos have a mass is consistent with standard model of particle physics, right? So, but it's much less extreme or exotic than postulating particles which are completely beyond the standard model of particle physics. So within Mond, we get a baryonic universe, which simply makes a lot of sense from the physics we know. There's nothing too extreme one has to postulate. And you have evidence for these stellar neutrinos not from the astronomy, but from the particle physics point of view. And that's important for the postulate that there's additional cold or so dark matter that only comes from the astronomical side. So there's no particle physics indication of additional particles, while there is indication for something like a stellar neutrino from the standard model of particles. So that makes a lot of sense from a physical point of view. And then I think the question was, and Milgrom will just in a moment jump in, but I think you asked also, how do we get out of this miserable condition?
Yes, that's the first question. Yes,
miserable for some, a heaven for others, right? Well, that is indeed the challenge. I am not hopeful. I'm actually, I mean, what I observe is that there are increasing number of extremely bright young researchers who actually see how to go forward, who accept that Mond is far superior than the other description, and who are available and ready and very interested. And that's the point. You have to be interested to learn to connect or to undo the laws of nature. And some such people do exist. They are very talented and capable. And that's a great hope. And maybe more and more such people are evident. However, the problem is indeed with the funding. It is a disaster. I mean, if I see how we have to beg for just little scraps of money here and there just to get another step of research being done, it's a pure disaster. Meanwhile, I'm seeing in universities hyper professorships being hired and created. That's a new thing, like hyper professorships being created, which get such incredible amount of money because they do quantum field calculations with dark matter. Yeah. And that's painful, that's pains. And because I do see the responsibility towards the taxpayer, and the taxpayer's money is something which we as scientists do have to take care of spending carefully and not wasting on abstruse ideas. In a sense, one can be hopeful. It is going forward. It's moving in the right direction, but there are massive problems, which I'm not sure one will be able to get away. I mean, to overcome. Yeah. So, Motti, maybe you wanted to
just to add to the issue of lensing. So, indeed, Pavel concentrated on non-relativistic formulation of Mond, which is good for describing galaxies where velocities are small. But for describing lensing, you need relativistic formulations. And there have been several such formulations, starting with tensor vector scalar theory of Bekenstein in 2004. There is the bimetric theory, and there are several other relativistic theories, and they all give lensing correctly, in the sense that they agree with observations. And in fact, there have been several tests of weak lensing in Mond, in the sense that, first of all, the profile that you get, there's a so-called galaxy weak lensing. I don't want to enter into exact description, but they essentially map statistically the gravitational field of galaxies using lensing to very large radii, several hundred kiloparsecs. So in the first place, the profile of gravitational field that is deduced from this is consistent with the predictions of Mond, and also the amplitude. So in some sense, there is something called the Tully-Fisher relation, or the mass-velocity relation, deduced from rotation curves of galaxies, and this kind of analysis extends it to gravitational lensing. And again, the results are in agreement with the predictions of Mond. So yes, Mond does account for lensing, can account, there are relativistic Mond theories that do. And another question in this connection was asked about the bullet cluster, well, also involves lensing. and which Pavel partially helped answered, I think. So the issue is the bullet cluster that is taken as the clearest evidence for dark matter is in fact not so. So even much before the advent of the bullet cluster, we knew that, as Pavel already said, that MOND does not explain away completely the mass discrepancy in clusters. It does reduce it by a large factor, but it still leaves systematically a discrepancy by a factor of 2 or so. And so the most mundane explanation for this would be indeed that there is some yet undetected baryonic matter in clusters. You don't need very much. It's very little in terms of the total baryonic budget that is needed in cosmology. And also we know that we cannot yet account for all the baryons we know exist in the universe. There is a so-called missing baryons problem. So we think we know the total amount of baryons in the universe, but we cannot account for it fully by just counting massive galaxies, stars, gas, and so on. So there's still about 30–40% missing, and only a small fraction of it could reside in galaxy clusters and explain the discrepancy. Now, the bullet cluster adds not much new to this, because if you take 2 such clusters with the still remaining discrepancies in them and you let them collide, you simply get the bullet cluster. So it doesn't really add to the problem. The problem being that MOND does not completely and fully explain away the discrepancy in clusters. But if there is some, as much as already detected matter in unseen baryons, it can explain both clusters and the bullet cluster. So.
Okay, thanks, Mordechai and Pavel, for the answers.
Stacy, do you have a comment on this?
Well, I wanted to amplify what Pavel said about the funding situation, because it really is, I think it is at this point, more about sociology than science. A long time ago, when I first got interested in MOND, having come from the background where I believed in dark matter, I wrote a proposal saying, geez, this theory had its predictions come true. We should look into that. And it was rejected, very harshly. And I thought, okay, the community is not willing to fund this kind of thing. This was almost 20 years ago. And so I basically did a global substitute, replaced MOND with dark matter, resubmit it the next year, and I got my money. That's basically the level at which this works. And Pavel's totally correct that scientists are focused on getting grants because that's what you need to support your students and your postdocs and getting the data and all those sort of things. And I would like to believe that that was an anecdote from the distant past, but I am aware of a colleague who had this experience very recently where this person did not even mention MOND in the proposal, but the panel came back saying, MOND is no good, you must not spend money on this. And the panel had associated with this person's name with having at some point written a paper about MOND and projected that onto this proposal that did not mention MOND. So it really is that bad.
Okay, thank you, Stacy. Next question is from Mikol.
Yes. Okay. Thank you, Pavel. Very nice talk. And I have a comment and a question. The comment is that you have highlighted the crisis in cosmology today and show the current debate that are open and still unresolved. About the dark matter, I fully agree, and there is not evidence about dark matter and no evidence of action can be found. So, okay. But about the current expansion of the universe, you just comment about it. Okay, so nice, but even the curvature of the universe, because it is very complicated to falsify it. For example, you cite the Leonora Di Valentino paper results, but it is very controversial because she used a Planck likelihood that the Planck collaboration say that it must be combined with other probes like BAO or CMB lensing to give right predictions. So even this debate is still very open. Okay, so it was the comments, and about my question. I believe that alternative approach to the Lambda CDM is very necessary, different perspective to resolve all the tension we see in cosmology and astrophysics. And but I want to ask you a comment about the models that are developed in this year about an interaction between dark energy and dark matter. Because it was developed because assuming the existence of a dissipation between the two dark components, one can explain the higher expansion tax today compared with what is predicted by the Lambda CDM anchored with the CMB. And so dark components are even evoked to solve problems, but we know nothing about these dark components. And so it sounds very strange. What do you think about it?
Well, I think it's important to try all possibilities. Yeah. So if somebody has a good idea, then it's important to forward this idea with calculations. The fundamental test bed is always, if I have an idea, is that idea already falsified by the available data? Because, for example, you could develop a theory of this, say there's this interaction between dark matter species, maybe with some dark photons, and that description will ultimately on large scale still be as good as Lambda CDM, but then it's already falsified by the existence of Gabi-Suwa. So I wouldn't continue with that research because it's basically pointless, right? Now the thing is that adding additional degrees of freedom into this dark sector is indeed an issue, right? I personally wouldn't do that because it's untestable. And it is very much reminiscent of adding epicycles, right? So because you have a framework overall and it doesn't fit, and then you add an epicycle. So for example, you add some self-interaction into the dark matter, or you add different dark matter species, which might have even a different thermal history or whatever, or you might add some additional, interactions or reactions between the dark matter particles and maybe a ray particle which would appear and then interact with a baryon or so. And that is no fundamental change because you're still within the overall framework as everybody else, but you're adding additional degrees of freedom. And that's very much the epicyclic approach from the past centuries, where one try to reproduce the motions of the solar system with epicycles on top of epicycles and shifts from the centers of where the epicycles are moving around, and then shifts on the shifts and so on. And that is just not. This is something as a scientist I personally wouldn't do. Yeah, but I wouldn't say that others shouldn't do it. But I definitely wouldn't. I think the universe, the data as I've seen them so far, is screaming to a massive change of paradigm. A really massive change of paradigm, which involves, and this is where Motti is himself not happy, and I know that basically none of the Mond community are happy about this. In my eyes, this might well include going away from a hot Big Bang. Yeah? That is, of course, very sacrilegious to say that, or how do you call it? Very much off the beaten track, but it's not without precedent. I mean, there are ideas of very bright researchers in the past who have been following such ideas. Now, it's clear that the universe is not steady state. I mean, that's, don't misunderstand that I'm trying to resurrect the steady state universe. However, some ideas by Dirac and also Hoyle and others are worth looking at. Yeah, that's what I'm saying. Maybe they can be discarded immediately as they were in the past. But given the current crisis, we really have to really try everything we can, even from the most fundamental, point of view. I mean, even really challenge and re-question our most cherished beliefs. Because remember, if you have a theory which explains the CMB, this doesn't mean that there might not be another theory which also explains it. And the dust theory might be such a theory. At least it definitely accounts for some aspects of the CMB. And the question is, can we exclude it somehow? But then the dust is simply there, and I just wouldn't know how to exclude that from the equation. So I hope this has been some sort of answer. I don't know, is that sufficient, or would you like to hear something else?
No, okay.
Thank you, Nicole. Next one is Indranil, please.
Yes. So there were some questions about if there's a definitive sort of test of MOND versus the Newtonian gravity that can be done in the future. And I'd like to mention a bit more about the wide binary test that Pavel touched on a little bit. So essentially the idea is you have stars separated by about 10,000 astronomical units, about 0.04 parsec. And there's many such wide binaries in the solar neighborhood. In MOND, what would happen is these stars would orbit around each other about 20% faster than in Newtonian dynamics. So basically at 240 meters a second rather than 200. And this kind of difference should be detectable with the latest Gaia data. The accuracy should be sufficient. So that's definitely not on galaxy scale. So the main advantage is that it's on a very small scale, where dark matter, even if it does exist, would not be significant. And another thing I want to briefly mention, which Pavel also touched on, is regarding the galaxy clusters and how MOND might be made to work there. So there's various possibilities, such as additional baryons, which have not been detected so far. I think one of the sort of best possibilities is to have these sterile neutrinos on top of the baryons. And if they have a mass of about 11 electron volts by c squared, then they would be able to account for the dynamics of various sort of relaxed galaxy clusters. But also that they will be able to account for the Buller cluster as well. So essentially the answer to how MOD might explain the Buller cluster would be very similar to the answer provided by lambda CDM. With these sterile neutrinos, one would also be able to get acoustic oscillation spectrum for the CMB very similar to lambda CDM, which we've discussed further in Hasselbauer et al. 2020, why exactly that is.
Okay, thank you, Indranil. The next question is from Thomas.
Yes, I would like to, I don't know, qualify the entire discussion a little bit. I mean, it's true that there are problems on small scales with lambda CDM, and you correctly, listed them beautifully and perfectly. And it's true that we have to think a little bit outside the box, but it's also true that there is tremendous success in the lambda CDM predictions of structure formation these days, right? And so far, we haven't really seen how the Mondian simulations actually reproduce all the observable scaling relations that we know of, right? So before we jump into saying that, the CMB is based on dust, we also have to check, what the scaling relations of the evolution of the structure in the universe that we can directly observe and study, right, out to redshift of 10 by now, is actually doing in this scenario, right? So do these dusty emissions are being fed by enough photons that are emitted from somewhere, right? And this somewhere needs to also form at earlier times, right, that we probably will also be able to observe. And so does that square with that model, right? So have you tested that? Have you looked into this in these simulations?
Yeah, so you started off with saying great success of lambda CDM on large scales. No, I would say not correct. So there is no, I just don't see the success, because this is what was part of what I was explaining, that where we have good data going on now out to gigaparsec and then even redshift of nearly 0.9, it's a massive failure. Wherever you look, wherever you really have quality data, it just doesn't work. Now, but you're absolutely correct. What we need to do is to redo all this amazing work which has been done in the standard of cosmology. I mean, that is, it's easy to, it's one thing to falsify a theory once it has been so hardly worked on that one can't falsify it. And so we can now falsify it even more rigorously because an incredible amount of work has been done on that, including the supercomputer simulation. They are truly very valuable. But it is indeed correct that we need to redo that in a different framework, and that is what we are now trying to do. So with collaborators in Strasbourg, in Chile, we are trying to now allow or organize simulations of structure formation in Mond on supercomputers. That is indeed the next step, but as Stacey was saying, this has to be funded. Yeah, that's the even more. I mean, that is actually the main challenge. It's not so much doing it because that is today quite easy. We know how to do it. We have the tools, but we don't get the money, and that's the problem. So by saying that Mond has to do all this, that is absolutely correct, but it's unfair because the funding is just not there to be able to do all of that. And you are absolutely correct with the dust. That is totally true. So Wawrzyk made some assumptions on how the dust at high redshift is heated from the stellar stars from the distant galaxies. And that has to be revised, I mean, rechecked. And I would be very keen to see these calculations being done independently of Wawrzyk to test on those results. That is essential, and to see how the initial assumptions might affect the results. So one aspect, for example, is that the stellar IMF would have been top heavy at a high redshift because of the low metallicity and more star bursting conditions. And so you'd actually get more photons than we expect. But we don't actually know really how much more because it hasn't really been calculated yet. But this would actually either maybe even destroy most of the dust. We don't know, right? If it's too much energy being produced, or even improve the estimates of Wawrzyk. And this is just one issue in this whole game.
Okay. Elizabeth, do you have another question?
No, I think we can wrap up here. Thank you all for participation. Thank you for joining us today for Pavel's talk. And thank you very much, Pavel, for taking the time to tell us about your work. Also, thank you the attendees and the panelists. Please be so kind and fill out the survey at the end of this Zoom webinar. And our next scheduled talk will be on April 16 by Joel Primack, Professor of Physics and Astrophysics at the University of California, Santa Cruz. And he will talk about new challenges in cosmology, galaxy formation, and planetary science. So stay safe, stay healthy, and until the next Golden Webinar in Astrophysics. And bye-bye, everyone.
Bye-bye.